Welcome to chapter 19, the first video for chapter 19 out of the book by Nate. So this chapter is all about energy, and the first law of thermodynamics is all about energy. So this video will introduce the first law, will introduce work and heat, and give more detail, especially with work. Heat we'll explore in more detail in the next video, and in particular the relationship between heat and temperature and heat transfer mechanisms. All right, so as the book says, it's all about energy. So heat, work, energy, a lot of these are interchangeable to people who haven't taken a class on thermodynamics. So this problem in purple right here is supposed to get you to think about some of the differences in how we use these terms. So 50 joules of heat are delivered to a gas, and yet the thermal energy of the gas only goes up by 30 joules. Why is this? So automatically this is saying, well, there's a difference between thermal energy and heat. And heat is a transfer of energy. So already this might be counter to how you use these terms. So we want to explore this conceptually, and the first law will actually allow us to make a quantitative statement about this as well. So where did that extra 20 joules go, for example? Okay, so like the book says, it's all about energy. And so one fact that you already know about energy is still true. Energy is conserved. We're not going to violate that. Energy is conserved. However, in this chapter, we're going to focus on a system. So this is just, this picture is just abstractly, we have some system, so some set of particles, and we have the surroundings. So the system, we'll look a lot at gases because we can talk, so solids and liquids are easier than gases. If you understand gases, then the other stuff will be easy. Gases, because they're compressible, we have to keep track of different kinds of energy a little bit more carefully. But the key thing to notice here with the difference between systems and surroundings is that energy can flow into or out of the system. Okay, so there's a flow of energy. So the energy of the system can change. So we're not violating energy, but we are allowing for energy to move between these two things. Right? So we want to keep track of, so the energy of the system, we can call this a few things. E with a subscript, SYS for system. Another thing that we can do is we can call this internal energy. So if you ever, so maybe you're looking at another textbook and they call it internal energy, it's the same exact thing. Internal means inside of this solid line that we drew for our system. So energy of the system, internal energy, same thing. And we're saying that it can change. So we'll have a delta E internal, or E system. So the key idea in this chapter, to kind of ruin the surprise, and this is, we'll get to the first law in about 1 or 2 lines from this. The key thing to think about is there's 2 ways of increasing the energy of this system. So let me give you one way. One way is to just take a flame and hold it next to the system. So suppose our system is at room temperature and we have a flame up next to it and we feel the system getting warmer and warmer. So that we'll keep track of as, that's energy in the form of heat. So that's an energy change that happens as a result of a temperature difference between the system and the surroundings. So if the surroundings are warmer than the system, then energy will flow into the system. And the other key way that energy can change, the energy of the system can change, is if we just do mechanical work on the system. So you can imagine someone comes and squeezes the system in, compresses the system, and it will actually warm up. So I don't know how intuitive this might be for you, but you take a piston, you squeeze it in, and the gas will warm up. Alternatively, if a gas expands really quickly, it can cool down. So yeah, we'll look at more examples of that later. Maybe one thing to think about is if you purse your lips and allow air to come out. If you just go with a wide open mouth, you'll feel warm air. but if you purse your lips and the air comes out, it'll feel cooler. So the reason for that is that gas is expanding. So if a gas expands, it cools down. Its internal energy goes down. But if a gas is compressed, its internal energy goes up. So this compressing, so if the volume of the gas is changing, that can be energy in the form of work. Okay, so to get to the first law, we need to replace energy of the system with so you learned, hopefully in a mechanics class, that you looked at two kinds of energy, nice energy and not nice energy. And these are the words that we have for that, mechanical and thermal. So remember in your first physics class, you talked about kinetic energy, gravitational potential energy, and that's all mechanical energy. And I say that it's nice because you can easily go back and forth between forms. Like you can go from kinetic energy to gravitational potential energy and then back to kinetic energy very quickly, so you can recover that energy. These chapters on thermodynamics, we're actually not interested in this one. So we're going to assume that this doesn't change at all. There's no delta E mechanical. So we're not looking at changes of mechanical energy. We're just looking at this not so nice energy. So we're saying that all of this energy change that could happen is going to affect this one. It's not going to go to kinetic energy of the whole macroscopic object. It's not going to go to gravitational potential energy. So this is what we're going to be focusing on in this chapter. And so we get to the first law of thermodynamics. This is delta E thermal. So notice how, as long as we can ignore this piece, delta E thermal, delta E system, delta E internal are all synonymous. So all three of this, and this are all going to be the same from now on. So keep that in mind. A lot of times we use these words interchangeably: E internal, E system, E thermal. But just keep in mind what we've assumed so far. So there are two ways energy can change. It can be because of a temperature difference or because of changes in volume. And that's really the main idea that we're exploring throughout the rest of the chapter. So for the rest of this video, so maybe this was the first third of the video. The second third is going to look at W in more detail. The third will look at Q in more detail. And then the fourth third, maybe I miscounted. The fourth third will look at combining all these and look at these energy transfer diagrams, just to keep track of all these things. Okay, so your book is just saying that there's more going on. The missing piece, heat. It's just slowly introducing the fact that you haven't considered heat yet in physics classes. Hopefully this stop to think makes sense. So in the picture, we have insulation surrounding the gas. That means that Q is 0. There's no heat transfer into or out of the gas. So if Q is 0, the only way that the energy could change is if work is done. And it looks like, so from this diagram right here, we have a force, an external force in the direction of the displacement of the piston. So the work done on the system is positive by that external force. And so if work is positive, the delta E is positive. So the gas temperature will increase. So your book is assuming something, right? We talked about energy, and this question is saying gas temperature. So they're already assuming you're comfortable with a fact. And let me be explicit and write this down. E thermal is an increasing function of temperature alone. So if you have a fixed number of gas molecules, the higher the temperature of those molecules, the higher the thermal energy. Okay, so E thermal is an increasing function of temperature. This should make sense. The word thermal means, it's very closely related to temperature, higher thermal energy. So right now this isn't maybe too big of a leap, but yeah, your book is going to assume that right away. The book alludes to it throughout and then gives an equation for it towards the end of chapter 19. So we'll be more particular with the equation for this later. but it'll involve things like heat capacities and things that we'll have to explore in more detail. Okay, the next section looks at work in more detail. So, work. So we're really going to focus on this thing, W. Your textbook is like most chemistry textbooks when it comes to thermodynamics, and not like most other physics books. And it has to do with a relative minus sign. So I want to go back and, so for this first law of thermodynamics, you might see it sometimes written as Q minus W. I'm going to add to that in a different color. So this is really confusing, right? So obviously this W can't be the same thing. If it is, then it's necessarily zero, and that wouldn't be very interesting. So what W means in these two expressions is very different. So this W on the right here, this minus W, this is work done by the gas. And this one right here is work done on the gas. So if we go back to our picture, I mean, if delta E is positive, so suppose Q is 0. Work done on the gas is positive means energy is being transferred to the gas. So this word on means on the system by the surroundings. So if work is done on the system, the energy of the system goes up. This W by is focusing more so on the gas, the work that the gas does on its surroundings. So if the gas is pushing outwards on the surroundings, it loses that energy in order to push outwards. So that the internal energy would go down if the work done by the gas is positive. So this is this is the book by Knight. If you've taken a lot of chemistry classes, this is the one that's common in the textbook. So the textbook eventually just calls it W. So this W right here is W on. And for the rest of the next couple chapters, anytime they have a W, it's W on, the work done on the gas by the surroundings. Whereas in a lot of other physics textbooks, so I'll write other physics textbooks, just other phys. So be careful if you're looking at other physics textbooks. You might see the first law written as delta E equals Q minus W. So what they mean by W is different. Right, so just a warning. Okay, so work you're used to as a force times a distance, just like this. And you're used to talking about the work done on a system by the surroundings. So, well, I want to be careful here. So let me start actually with work done by the gas. Right. So the work done by the gas will be, so this is the force. Okay, so we have our system. Maybe I should just redraw this thing, this picture. We have our system. And the system has some pressure P, which is pushing outward, right here. So you're used to seeing force dot distance here for work. But it kind of, for a gas, it's tough to talk about all these forces separately. The system has some pressure. In order to talk about the force right here, we have to take the pressure and multiply by the little area right here. And then we should sum up over all the areas to look at the total work that the gas does. So this isn't the most natural equation for work when it comes to thermodynamics. So what your book talks about is, instead of force times distance, it divides and multiplies by area. So F divided by area times area. And so it winds up being the pressure of the gas times any volume change of the gas. So notice how the volume change of the whole gas is the volume change of this boundary right here. And it'll go from some initial to some final volume. So the work done by the gas is integral of pressure dV from some initial volume to some final volume. And notice that because of this difference in the work done on the gas and the work done by the gas, if you're focusing on the work done on the gas, but you're talking about the pressure of the system, you got to be talking about, so work done on the gas is minus integral of from VI to VF, P dV. So the P is actually a scalar quantity. The pressure inside is equal to the pressure outside, more or less. I mean, they're basically at equilibrium, but even though this wall is moving a little bit one way or the other. So these pressures are equal, but it has to do with whether the arrow is in the same direction that the boundary is changing or not. What do I mean by that? So pretend this thing is expanding. Pretend that the gas is expanding. So the gas is pushing outwards, and the boundary is moving outwards. So the force, so that the gas is pushing outwards, it's moving outwards, the force times distance is in the same direction, work is positive. But that's work done by the gas. So if the volume expands, the work done by the gas is positive. And notice how this equation, if the gas expands, initial to final, remember these are volumes of the gas. If the gas expands, the work done by the gas is positive. The work done on the gas is the opposite of that. So if the gas loses energy, one way that we say that is that the work done on the gas is negative. Okay, so this negative is just addressing which way the energy is flowing. Now the integral of P dV, we can go back to PV diagrams. So remember PV. We always have some initial point and some final point. So what we're saying right here is that no matter what the path is, and remember, in order to draw a path on a PV diagram, this has to be a reversible process. And that was the statement that the arrows are equal and opposite in terms of the forces, because these are approximately in equilibrium at every step along the way. So you go to some initial to some final point. The work only is well defined if you have a path right here so that you can talk about the area underneath here. So if I'm going from initial to final this way, I can look at the area underneath this graph. So that area would be positive. So we're looking at area in the same way that mathematicians talk about area, in that it's positive if you're integrating left to right, and it's negative if you're integrating this way. So if the gas is expanding, notice how the volume is going up. If the gas is expanding, so I'll just say work by is positive in this case. Work done on the gas is negative. So these will always be opposite in sign. And the key thing to take away from this, if the gas expands, W by is positive, and W on is negative. And then if a gas contracts, contracts, so if its final volume is less than the initial volume, then the work done by the gas is negative. So really, maybe I just want to keep these statements right here. So if the gas expands, it's losing energy. It's doing work on its surroundings. The system is doing work on its surroundings. If the gas contracts, the outside, the surroundings are doing work on the gas. And the surroundings are increasing the internal energy of the gas by doing work on it. Okay, but notice how the magnitude of this depends on how you get from the initial to the final. So if I go this way, I would need to take the area underneath all of this. So it would be this area plus all of this stuff as well. So this path has, so work done by the gas for this path, call this path 2, is greater than the work done by the gas for path 1. Call this path 1, and this is path 2. And this would be bigger than 0. Okay. Now, so I think we're actually able to address this question right here, right? 50 joules of heat are delivered to a gas. So before we go on to heat, where are we here? Oh, so what your book does is it goes over W for some particular processes. So there's one that's especially important. If you have a vertical line, remember those were isochoric, W is 0. There's no work, there's no area underneath that isochoric process. So work is 0. So that means any delta E is just because of Q and not because of any energy differences from the gas expanding or contracting. And then a constant pressure process. So in this integral sign, a constant pressure process, you can take the P out of the integral sign, and integral dV is just delta V. So that's where this equation comes from. And remember, your book does W is W on, and that's where the minus sign comes from. Remember that the area is the work done by the gas. Okay, so this one is the area. So let me add this W by, this one is the area. Area under a P versus V graph. Okay, so if you take that area and you want the work done on the gas, you really have to include this minus sign right here, which is what your book does right there. Okay, and then isothermal process, you write P using PV equals nRT. So write it in terms of temperature and volume, and then if for an isothermal, T is constant, so you can factor out the whole nRT, and integral dV over V is log V. So you can get an expression for work explicitly in terms of the initial and final volumes. Okay, work depends on path. So this is what I mean by, so I wrote this right here for the two works. Your book gives another example right there. Okay, so to answer this question really quickly before we talk about heat. So remember the first law. So the first law of thermodynamics is delta E, so the thermal energy, delta E thermal, is equal to Q plus W. So this problem statement is actually pretty straightforward if you know the first law. And you keep track of these energies differently, right? The internal energy goes up by 30 joules, so this is a positive 30 joules, is equal to 50 joules of heat. And it's because the joules of heat are delivered to the gas, that means energy is going into the system. So this is a positive Q. Q is positive if energy is going into the system. W is positive if energy is going into the system. So solving this equation for W, it looks like W is equal to negative 20 joules. And remember this W, for the first law written like this is work done on the gas. This means the work done by the gas, would be plus 20 joules. And that only happens, remember, if the gas expands. So why is this? The reason for this is that, so you hold a flame to a gas, you're giving it energy in the form of heat. Some of that energy, 30 joules, is going to a temperature difference of the gas. So the gas is going to heat up and be higher temperature. But 20 of those joules are being used by the gas to expand against the surroundings. So why is this? The gas expands. Gas uses 20 joules to expand. That's why. So this comes from the first law of thermodynamics. We can solve for W, and W is because W is related to the expansion or contraction of the gas. So in this case, in terms of this energy flow, you're trying to put energy into the system, but the energy releases it just in expanding. So you're trying to give it 50. It uses 20 to expand, and the rest goes to internal energy. Right. Okay, heat. So you'll notice that the first law of thermodynamics is a statement about energy. So Q is energy. So heat, Q is an energy. So the SI units are joules. But a lot of times, so when heat was played with, when people were still developing the idea of heat and trying to make it quantitative, the unit calorie was developed. And so I just want to mention that 1 calorie, lowercase c, calorie, is 4.186 joules. So calorie has to do with water in particular. So it involves, a calorie is a nice unit of heat for how much energy it takes to heat up a gram of water by 1 degree C. And your book also warns you that, by the way, this calorie is not the same thing as if you look at the nutrition label of some snacks that you're eating, when you look at calories there with a capital C, that's a food calorie, which is 1,000 of these little calories. So food calorie is 1,000 times these calories, or 4,000 joules. So that's why I was very careful to write a lowercase c, because a capital C means food calorie. And then your book says we're not going to use it in this textbook, but you want to be familiar with it if you're looking at food packaging. Okay. Yeah. So they're saying a lot of garbage. So what they're saying is important, but I want to say it in a slightly different way. I want to look at maybe these two processes again, and I want to focus on something else about these two. So let me rewrite a process like this, but in a slightly, being a little bit more quantitative. Okay, so suppose we have a gas. So everything we do in this chapter and the next few are going to be through PV diagrams. They really help us see what's going on, and you can see that with the work equation, areas underneath the paths here tell us a lot. Okay, so we're going to have an initial. Let's for fun, let's just go initial point here to final point here, just to be a little bit different. So here the gas is going to contract, and so you should already know which way energy is going to go. So it's going to go from the system to the surroundings, or W is negative, right? W on is negative. So we can imagine so you can go from initial to final a bunch of different ways, a bunch of different paths. So you can do one of them this way. And let's say the work done on the gas here is, and notice the gas is compressed. I forgot what I said actually. The work on the gas is definitely positive in this case. So this would be a negative area. The work done by the gas is negative. The work done on the gas is positive. So let's just say that the area underneath here. So if we were to be careful about this, a lot of times in problems you have nice shapes here, so you can actually calculate the area if you knew the units here and the units here. Let's say that we're able to do that, and we see that the area underneath there was 20 joules in magnitude. And the work done on the gas is positive in that case. And then let's look at another process where, well, maybe I want a color button. I can't even tell if that's green or red anymore. Let's say this process, the work done on the gas would have to be bigger in magnitude. Remember, W on is minus work done by the gas, and work done by the gas is the area underneath. So that area is going to be bigger in magnitude. Let's say it happens to be exactly twice that, 40 joules. Okay. And let's also say, okay, so we have two different, so we'll call this path 2 in black right here. And I think in purple, we'll call this path 1. Okay, so I want to focus on a few things. Okay, so I want to do two things. One is I want to compare paths 1 and 2, and then another is I want to draw an energy transfer diagram. So I want to draw something like what's going on in this book. So first, let's compare paths 1 and 2. Right? So the W's are different, but I want you to see that they have the same initial and final points. And there's a very special fact that we can say because of that fact, and that is that the change in internal energy is the same for both. Delta E internal is the same for paths 1 and 2. So why is that? Well, remember that E internal is a function of temperature alone, So both of these processes, whether you're looking at path 1 or path 2, they both start at the same initial temperature. So remember there's a hyperbola that goes through this point. This initial point is on this isotherm, this initial isotherm, and then both wind up on the same final isotherm. So call this E thermal initial and E thermal final. So E thermal, by the way, notice how I called this internal energy, but I called it thermal energy right here. So I'm using it interchangeably. So I wrote it thermal, but I mean the same thing as thermal right here. It's the same for both of these, and it's going to be negative for both of them as well. So delta E thermal is negative for both. Okay, and it's the same for both. So we call thermal energy something called a state function. Another way of saying this fact is that E thermal, this quantity, is a state variable. It depends only on the point and not on the history of what happened to the gas. So work is a path-dependent function. So you see path 1 versus path 2, the work is different. The internal energy only depends on what point you're at in the PV diagram. It doesn't matter what happened all the way up before that point. So because of that, there's some E thermal here and there's some E thermal here. And the difference between those two is just some value. And it doesn't matter what path you take to get from I to F. Okay, so these two things are saying the same thing. Okay. So let's focus now just on path 1. So I'm going to go back to this purple. But you can make a similar statement for path 2. Okay, so for path 1, the first law of thermodynamics is true. It's true for whether you take either of those two paths. So for path 1, delta E thermal is Q, the heat added to the gas, plus the work done on the gas. So I'll try to write the subscripts as much as possible. For the most part, if I don't write the subscript, I'm going to use the convention that Knight and chemistry textbooks use. At least for chapters 19 and 20, 18, 19, and 20. It turns out that for engines and refrigerators, most of the time we're going to be concerned about work done by the gas, so I might switch over at that point. But really, I'm going to try and write the subscript as much as possible. So I want to point out that we can say something about Q for this. Even though we don't have any equations for Q, we can say something about Q because we know that for this problem, so this quantity is negative. The work done on the gas is positive. So I have a negative number is equal to something plus a positive number. So that something had better be negative and bigger in magnitude than W on, right? In order to get an equation like this. So I have to conclude that this is going to be a big negative quantity. Negative plus a positive number is equal to a negative number. So that negative is big in magnitude. So for path 1, I can draw what's called an energy transfer diagram. And this will be the last thing we do. So the energy transfer diagram is keeping track of the energies. So your book does it for a few of these processes. We're going to talk about it for path 1 right here. So they have some zero line. 0. We're keeping track of E thermal plus E thermal initial plus work plus heat is equal to the final amount of thermal energy. Okay, so do color consistent with your textbook here. So the W and the Q's are changes in energy. And it looks like from this equation I have the work done on the gas is positive and a little bit compared to the other one. So this is going to be some positive quantity. So this right here is the work done on the gas. But the heat delivered to the gas is negative. So in other words, if you say that the heat delivered to the gas is negative, that means that heat leaves the system. Energy in the form of heat leaves the system. So in other words, along the way, along this path 1, Q overall was negative because the overall the gas had a higher temperature than the surroundings. So because of that, energy left the system. So remember that you're in equilibrium at every point along the way. So you're approximately in equilibrium, so the temperature difference is very, very small. But during these small steps, the energy is leaving the system, despite the fact that the temperature difference is small. It exists to leave. So for that energy to leave. Okay, so Q is negative and bigger in magnitude than W. So no matter what thermal energy we started with, so this is the initial amount of thermal energy, it looks like when we add these two, overall it goes down. And that's why, so our final thermal energy would be something down here, so E final. So what we just drew was an energy transfer diagram. And this is thermal energy initial and thermal energy final. It's an energy transfer diagram. And your book is big on these because it really wants you to understand what's going on from an energy point of view. Yeah, so we'll look at some of these processes later. Your book highlights these three processes because for the third, the first law of thermodynamics involves these three terms. There are three processes that involve one of these being zero. So isothermal has this one being zero. Isochoric has this one being zero, and then adiabatic is one that we're going to encounter later in this chapter, and that one involves Q equals 0. All right, that was a lot of info, so we're going to spend the rest of the chapter getting used to this as well.